So,
Okay, so
thank you very much, Anna, for your lecture, and the floor is yours.
okay, thank you. Let me share my screen. Can you see my presentation?
Yes, perfectly, yes.
Okay, so thank you very much for invitation for presenting. Just so everyone knows, this is the first lecture of this type that I'm giving, so you're gonna be kind of my guinea pig for giving lectures like this. I hope it's gonna be well fitted, and I try to give in a presentation the general overview of the method. I call it basics because the method is quite big and you can talk about this a lot. I don't know all of your backgrounds, so I try to go from quite basic information slightly to more advanced. So I hope you're going to be able to follow it and get something for each one of you from the presentation. So I had the first slide showing my background, but this is actually what Odile just said. So I'll go like briefly through this. As Odile said, like I did my master in civil engineering. I was specializing in bridges and underground structures. During my master degree, I spent a year in Norway, in Trondheim, at NTNU, where I wrote my master thesis, and I was working on I did the thesis on the tunnel construction site, which was quite interesting. I defended back in Poland. I worked for a bit in both on the construction side and in the design office, but it wasn't really my cup of tea. So I decided to do a second master degree, and I moved to France, where I did my master degree in geohazards at University Grenoble-Alpes. I thought I speak French. I don't. That was clearly noticeable when I moved to France. I did my second master degree in New Zealand. In a project connected with GNS Science in Wellington in New Zealand when we were working on the earthquake recordings in buildings. And this was actually something that really got me into seismology. And I was also encouraged to apply for the PhD in engineering seismology. So I joined the ITN Urbasys EU, and I got a position in Trieste in Italy. And as Odile said, my thesis was focused on approaches for structural soil structure interaction assessment. And I was looking more how buildings radiate energy during shaking caused by an earthquake to surroundings ground. I defended in 2023, and basically right after I moved to Germany to start my first postdoc at BAM, and this is what I'm currently doing. I work with Acoustic Emission. As you can see, this is also kind of a new field for me. I didn't do this before, but as you will see in this presentation, it's quite closely related to seismology. So it wasn't a huge change, but still somehow a new thing for me. So a few words about BAM. I think most of you are familiar with the Institute because you've been there, but just a quick reminder for those who don't know it. So BAM is a material research center. We are located in Berlin, in Germany. This is the main entrance. This is actually our building where we work. The organization is quite big. We have 11 departments divided into 75 divisions and sections. And these are the informations from our official information center. We have around 1,550 people, including trainees, PhDs, students, postdocs, and from more than 55 nations. But I'm in division 8.2, whose head is Ernst Niederleitinger, which you probably know. And our group is called Non-Destructive Testing Methods for Civil Engineering. We're a group of around 28 people, including scientists, postdocs, PhD students. We have also some master's students and student assistants, and obviously technical staff without whom we wouldn't really succeed much. Our main fields of application are non-destructive testing methods for infrastructure and existing structures. We also focus on methods in nuclear waste disposal research and decommissioning. And we have also a group working on new materials and construction methods. So that's just a brief introduction. And coming to the content of this presentation, I'll go through what we're going to do. So I'm going to start with the general overview of the acoustic emission method. I will give you some definitions, a little bit, not too much, brief history, and some examples of applications. Then I'm going to go to the instruments and measurement process. I will talk a little bit about the sensors, the equipment that we use during the measurements, and how we actually use them. Then we're going to go through the signal characteristics, both in the time and frequency domain. I'll also show you the how acoustic emission fits in the context of seismology. And I think after that, we're going to do a small break. I don't know how long, but I think it should be around 15 minutes. It's up to whatever the schedule we can see. And then we're going to go into parameter-based acoustic emission analysis. I will talk about signal parameters, a Kaiser effect, a classification of acoustic emission signals, and B-value analysis. We're going to look afterwards in the different types of approaches, which are signal-based. This is quite a wide subject, so I will just scratch the top of the iceberg. There's a lot of things to talk about, and this could be a bunch of lectures on its own. So I will just give you a brief overview of waveform analysis and also quantitative analysis. Then we're going to just also scratch a little bit of another big topic, that is source localization. I'll give you a general overview of the methods that are used and talk a little bit more about the commonly used one that is called Geiger's method. And with this, I will sum up, give some conclusions and a small outlook. What are still interesting hot topics in terms of acoustic emission, which could be developed much more. Okay, so coming to the first part, I will start with the general overview. So when we say acoustic emission, what we actually think about, there are some very defined definitions about this given by two standard office. So first one is coming from American Society for Testing and Standards, and it's acoustic emission is defined as a class of phenomena whereby transient elastic waves are generated by the rapid release of energy from localized sources within the material, or the transient waves so generated. Okay, so this one is long and maybe not the most clear one. The European Committee for Standardization, on the other hand, says that this is a transient elastic wave generated by the release of energy with the material or by a process. And what it means that we have, for example, a beam, we have sensors, we apply some kind of a force on it, a crack appears, which emits acoustic emission waves. So this is a very simplified definition of this. So we can, in simple words, say that acoustic emission describes the spontaneous release of localized strain energy in stress material. I'm not going to go super deep into history, but just give you a quick overview when the study started, how it started and from where. It is considered that the acoustic emission technology began to be investigated in the middle of the 20th century. First, and all this mention are coming from around 1933, where Kishinue, sorry for the pronunciation, delivered the first and the oldest report on scientifically planned acoustic emission experiment. He was studying timber creaking prior to break, and this is where the first mention come from. Later, in 1936, the German scientist Förster was looking at the acoustic emission phenomena in wire-shaped nickel steel specimen, and they made the electrodynamic transmitter-receiver system to transform mechanical vibrations into electrical voltage. So this is where they were working also in this area. And then also in the 30s, in 1939, this was first studies in the geological field, where Albert was working on the seismicity activity in rocks. And since this is very similar to acoustic emission phenomena, this is the first mentioned in that terms of geology. It's been often quoted that acoustic emission history started in 1950 with the publication of Kaiser dissertation. He was working in the using a metallic specimen, and he is the father of a concept of irreversibility called Kaiser effect, which I will later talk more. From other, oops, why it's not working? Oh, okay. And the later mention was by Lermite, and again, sorry for my pronunciation, where he was actually working on the and showed the relationship between acoustic emission, the decrease of ultrasonic velocity, and the increase at the same time of the Poisson ratio and axial strain. So this was one of the more important works as well in this terms. But the term of acoustic emission was actually first used in 1961 by Schofield, and since then it's in general in use. In the coming years, there were a few groups, like between 1969 and 1972, a few groups working dedicated to acoustic emission were created. So Acoustic Emission Working Group, the one in the US, a Japanese Committee on Acoustic Emission, in 1972, European Working Group on Acoustic Emission, and from 1972 started the International Acoustic Emission Symposia, which led us to the latest history event in 2016. There was created an International Institute of Innovative Acoustic Emission, coordinated by the three groups that I mentioned before. So obviously this is just very selected and brief history, but to give you an overview when it started and how it goes, there it is. Okay, so probably you're quite aware of that there are different techniques in non-destructive testing. Some of them we can like very roughly divide them into active and passive techniques. They differ in a sense where the source is coming from, and in active methods, the source is emitting the waves is generally applied to the material, and then it's received by a receiver. But in passive techniques, which acoustic emission belong to, the sources are within the material. They are quasi-produced by the material itself due to some kind of loading. So this raises a question: is acoustic emission really non-destructive, since we need some kind of active deterioration, a fracture, a process of the material for the testing? But in general, we don't destroy with the method itself. So like in general, this fits into non-destructive testing methods. And acoustic emission is also usually applied during the loading, whereas most of the other NDT methods are applied either before or after loading of the structure. To come to sources, this is just, I'm going to give you just some examples because there are plenty, and it's just an overview. So as you probably figure out, I'm coming from the background when we use concrete as a main material for testing. And in concrete, acoustic emission comes mostly from the crack formation or plastic deformation due to aging, temperature gradients, or external mechanical forces. For example, also rebar corrosion and failure, and interface condition between concrete and rebar, or for example, in pre-stressed concrete in bridges, for example, breakage of tendons. But there's also a lot of other areas where we use acoustic emission testing, for example, in metallic materials, and there the main sources of emissions are due to initiation and growth of cracks, particle fracture, sliding and dislocation movements, twining or phase deformation. Other group of materials are composite materials, and for composite materials, fracture may refer to the generation and propagation of cracks within the material matrix material, along the matrix fiber interface, or due to the fracture of single fiber or as a bundle. Another highly relevant source of acoustic emission found in fiber reinforced polymers is the friction of existing crack surfaces. And this occurs often during loading and reloading of damaged composites. There's also a bunch of so-called pseudo sources. This could be liquefaction and solidification, friction in rotating bearings, solid-solid phase transformation, leaks, cavitation, realignment, or growth of magnetic domains. As I said, there is much more. We have also ceramic materials, wood, and so on. So this is just a few examples of the sources. Coming to applications, the method can be applied from very, very tiny laboratory experiments to big monitoring applications like bridges or wind farms. It's also used in seismology in lab experiments. Since it's so similar, acoustic emissions are used to mimic earthquakes in labs. And here I just give also examples. I bet you can find also more, but just to give you the general overview where you can actually apply that. So our main interests, for example, bridge and buildings, but there's also a lot of studies done on wood and timber structure, weld monitoring, pressure vessels, monitoring corrosion. A big part is in monitoring condition of wind turbines, pipelines. The other day on a conference, I saw a really nice presentation about use of acoustic emission for monitoring of cultural heritage objects. Big area is aerospace engineering, and as I mentioned before, earthquake research. So to sum up the first part, the key takeaways are that acoustic emission is the spontaneous release of localized strained energy in stress materials. And this energy release can be due to multiple factors, for example, microcracking in the material, and it's recorded by sensors attached to the material surface. It's a passive method, so the sources are within the material, and they produce a quasi test signal for testing. And acoustic emission sources varied. It can be due to multiple reasons like crack initiation or propagation, matrix and fiber breakage, slip and dislocation movement, and many more. Okay, so since we have the general overview of the method, we can go to more detailed. So we're going to talk a bit more about the instruments and measurement process. So to measure acoustic emission, first thing we have to do is attach the sensors, but the sensors on their own don't do anything. We need to attach it to other components of the measurement chain, which in case of acoustic emissions are preamplifiers, which then are connected to a data acquisition system connected to the computer. In the measurement process, as I mentioned before, we apply some kind of a force or some kind of a process to our test object. Some kind of a crack or thing emitting acoustic emission waves appeared, and the waves are emitted inside the solid towards the sensors. Acoustic emission signals then are detected by the sensors as dynamic motions at the surface of a material and are converted into electric signals. Then they are amplified by the preamplifiers and filtered, and then stored and recorded by data acquisition system. And in the end, we're doing the analysis on the computer. And this all is, all of this measurement chain introduces some kind of a transfer function to it. So basically, what here is important to remember that what we actually, what the signal that is coming from the source is not exactly the signal that we're gonna record and analyze on our computer. There is a bunch of steps on the way which modify the signal, and I assume that you're all connected, not connected, you're all familiar with the concept of convolution, because each one of those steps is contributing to the final record, and the final recorded digital signal is a convolution of all of those steps. So we have the initial source signal, then we have the the Green's function describing the wave propagation in the medium between the crack and the sensor. Then we have the transfer functions of the sensor itself, and then the data acquisition transfer function, including preamplifiers and filters. I will not go into much details about this, but it's just to remember that we have to keep it in mind when analyzing the signals later on. How the acoustic emission sensor look like? This is a graphic showing it. So we have a wear plate, we have a piezoelectric element and connector. It's all like put in a housing that is securing the sensor. The sensors work in a way that they transfer surface motions into electric signals. They generate electric field when they undergo deformation. And usually the type of the transducer that are used almost exclusively in acoustic emission testing are sensors that exploit the piezoelectric effect of PZT elements. So this is a lead zincronate titanate element, which transfers the displacement into voltage. The most common type are the contact type. And the piezoelectric sensors are used since they are best combination of low cost, high sensitivity, and ease of handling and selective frequency responses. We have two different types of sensors used in acoustic emission. One is resonant and one is broadband. And those are the differences between them. The resonant sensor has the narrow frequency response. It has a peak sensitivity higher than the broadband, but it's narrow. The size of the piezoelectric element inside defines the resonant frequency. So basically, for smaller piezo elements, we have higher resonant frequencies, and the bigger we get, the lower resonant frequency we are obtaining. They operate usually in the range between 150 and 300 kilohertz, and yeah, this is an example of a sensor. I think this is the one that is quite commonly used, RR15, the type of the sensor, and this is its the blue line is its response function. So you can see it has a peak, and then the other frequencies are de-amplified. The other type is the broadband type of sensor. They have considerably flat frequency response. It's not really flat. It has some kind of peaks and troughs, but it has a quite wide spectrum range, which so that means that it can it's sensitive to quite a lot of frequencies. However, it has a lower sensitivity compared to the resonant frequencies, meaning that the lower voltage than resonant sensor for the same displacement. And it's often used, this is just a general idea, that it's used when the frequency analysis is required in the signal post-processing. So sensors have to be somehow attached to the specimen, and this is a very important part of the measurement process, because the coupling between sensor and the specimen is very important due to the very low amplitudes of acoustic emission signals. It should reduce the loss of signal energy and should have a low acoustic impedance compared to the material to be tested. And if we want to avoid the attenuation of the signal, it's necessary to avoid air bubbles or thick glue couplant layers. Also, the surface before mounting the sensor should be smooth and clean to ensure the good adhesion. And one of the most important things that sensors, acoustic emission sensors, have to be always stationary. They should not move. They should not be able to displace during the measurement process. And this is an example of influence of different couplants on the sensitivity of acoustic emission sensors. And we have different ones, but what I want to stress out here is this gray dashed line. And it shows that this one is like this couplant, which is actually dry contact, so without anything between the sensor and the specimen, shows how much of the energy of the signal we're losing if we don't provide a good coupling between the sensor and the surface. So this is some examples of how acoustic emission sensors are mounted. So for example, we can attach them directly with wax or hot glue for example, on concrete or on metal. So they're fixed with the measurement surface to the specimen. If we have some kind of metallic surface, we can also use magnetic clamps. So you have magnetic clamps, the sensor is in the middle, and it's pressured to the surface by a spring. Or, for example, if we have a beam or something that we can wrap around, we can use also a tape and some kind of grease connected to the on the surface, on the connection between the sensor and the surface. Important thing to keep in mind when doing acoustic emission measurements is also the aperture effect. In plate structures, we assume that the wave direction is predominantly parallel to the sensor surface, which is different in bulk mediums, like, for example, concrete blocks, where the wave comes at an angle or even at 90 degrees if the source is deep enough in the side of the material that we can assume so. And the aperture effect is the decrease in the recorded wave amplitude at high frequencies due to multiple wavelengths being averaged over an area of contact of the sensor. And this directly affects the sensor sensitivity curve, since it might differ depending on the excitation location and sensor diameter. Again, the reason is connected to the diameter of the sensor, since the voltage is an integration of the response of the whole contact surface. Or in other words, the voltage output is derived from the average disturbance over the whole surface of the element. And therefore, the larger the surface area, the higher is the possibility to interfere with the waveform shape. So this is an example. So for example, we have a sensor that is like much lower, like smaller than the wavelength, and the waveform is accurately depicted. However, if we have a big sensor and with higher frequencies, the waveform is cancelled due to successive cycles. So this is something too important. And this is an example of this phenomena in a simulation. So basically, we have a metal plate, we have some kind of excitation, and those are 3 snapshots in 3 different time steps. And the assumed are 3 different lengths of the sensor. So we have a point sensor of 1 millimeter, medium sensor of 10 millimeters, and long sensors of 30 millimeters. And on the right, you can see the waveforms recorded by the sensors and corresponding Fourier transform. And as you can see, the point sensor exhibits by far the highest amplitudes as its whole surface area, in this case, the line in the 2D simulation, is excited at the same phase of the wave. However, the long sensor, so the black line, exhibit much smaller amplitudes, since even when the maximum pressure of the wave is exciting a part of the sensor, this is averaged along the whole sensor length, with the other parts of the line sensing less pressure or even opposite phases. So we can see, like in the top row, we have excitation of 1 megahertz. So this is the high frequency, and the bottom part is the 100 kilohertz. And we can see that actually the higher frequencies are much more affected by this than the lower. And we don't see anymore the main peaks. In lower frequencies, we have the strong decrease in amplitudes. We still kind of have the peak at the main where it should be, but it's worth keeping in mind to choose the right sensor for the right application. Okay, so I was talking that we have mostly contact type sensors, the piezoelectric sensors, but there are also alternative acoustic emission sensors that are used for studies. They're not commonly used, but there are some. There's research going with different types. So, for example, optical fiber sensor or laser acoustic emission system, which is a bit tricky because the signals are relatively low, and this is maybe not as sensitive as the contact type. And the third type that is actually used a bit more in the research and has quite good potentials are embedded sensors. So for example, this is the sensor that was developed in BAM, and it was actually employed in a recent research where the sensors were embedded during the concreting of the beam, and they can be used easily as acoustic emission sensors. This is also piezoelectric sensors, not just embedded. Okay, so that's all about the sensors. We have also in the measurement change, we have amplifiers. They are used to magnify weak acoustic emission signals. And this is also important that the cables from the sensor to the amplifier are subjected to electromagnetic noise. So we have to use short, specially coated cables to minimize this effect. And amplifiers have preferably a flat response in the frequency range, so they don't introduce much of the change of the signal recorded. They have gain in decibels, and they should contain state-of-the-art transistors that minimize the electric noise. This is important part, but not much more to say here. We apply also the filters. I guess that you're familiar with filtering of the signal. Just to say, we use different filters depending on the noise level or attenuation property of the material. I think this is not new to anyone, but just to give you the example how the filtering affects the acoustic emission waveforms. So you can see the more we filter high frequency, the flatter response we get. And this is basically what we can do. We can cut the different frequency range to obtain different frequencies of interest of our signal. And the final part is the data acquisition unit. This is a part which is basically the mastermind of the data acquisition. Obviously, it converts the signal from analog to digital. It's responsible for triggering data recording. Data acquisition system in acoustic emission also are responsible for anti-aliasing filtering, and in some cases also the parameter analysis. So to sum up, we have commonly used acoustic emission sensor are the contact piezoelectric sensors. We have two different types of sensor. They're resonant and broadbands. And the proper coupling of the sensor is very important for proper data acquisition. And sensor must be always stationary. The other thing, since acoustic emission signals are weak, it's to improve the signal to noise ratio, we use preamplifiers, and the data conversion from analog to digital is done by data acquisition system. Okay, and the last part before the break, we're gonna talk a bit about the signal characteristics. First thing, the frequency range where we operate, we're in the ultrasound range, and acoustic emission fits in this kind of range from 20 kilohertz to 2 megahertz. 2010, this is the lower band is more or less in this area, and this frequency range is chosen due to the low frequency content of elastic waves is only a little affected by the attenuation process. So this is where we starting and then we going up, but this is maybe not the most important, part. But we have, in time domain, we have two different types of acoustic emission signals. We have burst signals that are non-repeatable and occur discretely. So this is the type of the signals. We have the bursts in here, and they are independent in time. They coming from crack growth, corrosion, local catastrophic yielding, etc. And the other type is the continuous acoustic emission signals. Those are transient bursts and are not discriminated. They are produced by numerous of overlapping acoustic events, and this is, for example, caused by friction processes, leakages, and so on. And this just gives an idea that the signal contains information about the source that caused them. We measure signals in voltage or decibels. The relation is as follows. So we can convert one to another. So in this case, it's the measured voltage. We have also the reference, usually it's 1. And the the energy is the integral of the rectified waveform envelope. To give you some kind of an idea how big I say that the acoustic emission signals are weak, but to give you the idea of how weak, this is, for example, if we have a mosquito that is directly flying on the surface of the acoustic emission sensor, this will be still at 10, the order of 10 magnitudes more energetic signal than what we are able to record during acoustic emission testing. So we can see that the method is very sensitive to very small energy signals that we can obtain. And as you know, like my background is in seismology, so to give you the general idea how acoustic emission fits in the context of seismology, like as most of you know, an earthquake is a sudden movement of earth crust that generates elastic disturbances known as seismic waves. And those waves propagate spherically outwards from the source and vibrate on the ground. And those vibrations can cause damage at the Earth's surface, which can be then correlated to the magnitude of the earthquake or the local condition when this is appeared. Acoustic emission, on the other hand, is as we mentioned before, is the spontaneous release of localized energy in stress material. And this energy release can be due to, for example, microcracking in the material, and can be recorded by the transducers attached to the material surface. So as you can see, the acoustic emission are so similar to seismological technique because they basically apply the same concept, but at a different scale. So this is a graphic showing where we, on the frequency range, where we're talking about the seismicity of the Earth, we kind of operate in the range up to 10 Hertz. When we talk about acoustic emission, we are moving much higher in the frequency range from 10, 20 kilohertz to 1 to 2 megahertz. So this is quite similar. What we also see that, for example, this is an example of a seismic wave recorded from an earthquake, and as on the right you can see the acoustic emission wave. I don't know if this is very visible, but you can see that definitely the time axis is different. We're talking here about seconds, and in acoustic emission we're operating much smaller values. But what we're looking for inside is quite similar. We have in seismology we're looking for hypocenter location, whereas in acoustic emission we look for source localization. We have common fault types. In acoustic emission, we're looking for fracture modes. So although there are differences in scale, space-time, geometry, loading, boundary conditions, and the medium, basically earthquakes and mining-induced seismic events and acoustic emissions are similar phenomena. To give you also like the overview, so for example, if we look at the energy moment relationship of acoustic emission, they show similar trend as, for example, mine seismicity events or natural earthquakes. So they follow the same patterns. And as mine seismicity, they're independent on the moment. The stress drop and the moment are independent. So basically, this shows a very similar relationship. So to sum up this part, we have key takeaways here. So acoustic emission signals are in frequency range from 20 kilohertz to 2 megahertz, 10 to 1, depending on the sources. We have two types of acoustic emission signals, burst and continuous ones. We measure acoustic emissions in volts or decibels. And although there are differences in scale, space-time, geometry, loading, boundary conditions, and so on, earthquakes, mining-induced seismic events, and acoustic emission are similar phenomena. Okay, so I think this is a time where we will make a small break.
Okay, thank you very much. So I stop the recording.
Mm-hmm.
Let me see.
Okay, can you see my screen?
We can.
Yeah. Okay. Okay, so the second part of the presentation, I will start with the parameter-based acoustic emission analysis. So the general idea behind the parameter-based analysis is that the signal can be sufficiently described by the set of characteristic parameters or so-called features, and storing the whole waveform is not necessarily. We can just store a small amount of information, which consumes less time and less space, and we can still do the analysis of the signal. I will use here two different terms, which I want to say in the beginning. So first is a hit. When I'm gonna say something is, when I'm gonna refer to a hit, I mean a signal that exceeds the threshold and causes a system channel to record the data. And event is a bunch of hits coming from the common acoustic emission source. So this is just two different definitions. So let's start with the general parameters and what are they. So first one is the threshold. This is a predefined voltage that must be overpassed by the incoming waveform in order to trigger the acquisition system to start recording. It also helps to avoid the low amplitude signals or noise, and we only keep the signals that are within certain, which are crossing the given threshold. Then we have the threshold crossings, which are called counts, and those are the numbers of times within the signal where the threshold is exceeded. So basically, whenever the amplitudes are crossing the threshold, we say it's a count. So like almost every acoustic emission parameters, counts are strongly dependent on the level of the applied threshold. And what we call the threshold between the first onset, so the first crossing until the peak, are called as counts to peak. Another thing is the amplitude. So basically, it's nothing surprising. It's the peak voltage of the signal waveform. It can be either positive or negative. It's closely related to the magnitude of the source event, but it's also important to remember that the farther we go from the source, so if we're going to increase the distance, the attenuation will strongly compromise the final amplitude at the sensor. Another thing is the duration, and this is the time interval between the first count and the last threshold crossing. So this is generally expressed in microseconds, and is connected to the source magnitude and type of the event. Another parameter is so-called the rise time, and this is the time interval between the first crossing and the peak amplitude. This is closely related to the source times function, and it's used to classify the type of the fracture that I'm gonna speak a bit more in a second. Another thing, another parameter that we use is energy or the signal strength. And the definition of this differ in different acoustic emission system suppliers, but generally it's defined as a area, measured area under the rectified signal envelope. And the energy is preferred to interpret the magnitude of the source event over counts because it's sensitive both to the amplitude and the duration, and it's less dependent on the voltage threshold that we use or operating frequencies. So this, and the last part that is kind of on the edge of time domain and frequency domain, it's so-called average frequency, but it's defined as a number of threshold crossing over the duration of the waveform. So this is just how many times during the duration of of our signal we crossing the threshold. Another parameters, there are two parameters that we extract from frequency domain, meaning from Fourier transform of our signal. This is a peak frequency, which is basically the maximum magnitude of the frequency spectrum. And we have also commonly used, it's a central frequency, which is defined in this way, where we have a frequency and the magnitude. And this is also a quite commonly used parameter in the analysis. Okay, but that's great. We have a lot of parameters, but so what? The idea is that using those parameters, we can do the quick estimation of the character of the event. For example, we can evaluate the fracture mode. So this is an example. In the top row, we have an idea of a tensile crack, which is it's a case of a normal crack due to bending, and it's actually characterized like there's a lot of studies trying to put the certain parameters that are characterizing the this kind of fracture, and in general, in a like very simplified way, the tensile cracks have a higher proportion of longitudinal waves, meaning that they have a shorter duration and shorter rise time, and this can be differentiated between the case of the shearing action, which is shown in the bottom part, and this means that the slides are moving parallel, but at opposite direction. So this is basically the definition of the shearing crack, and it's characterized by the higher proportion of shear waves, which are slower and arrive later. So for example, we have different parameters. So in general, we can classify it based on the idea that the tensile events emit higher frequencies and shorter waveforms due to the higher proportion of the longitudinal waves over the shear waves. And most of the energy arrives within the waveform, within the early parts of the waveform. And this, as I mentioned before, results in the shorter duration and rise time. Therefore, parameters like average frequency obtain higher values in this parameters. In contrast, so in the shear events, parameters like duration, raise time, or raise angle. So this is basically this part, the angle between the amplitude and the rise time, show higher values. Because the major part of the acoustic emission energy goes into the formation of the shear waves, which are slower and arrive later, and so on. So this is basically, we can use those parameters in a very simplified way to classify the fractures. So this is an example, for example, from the 4-point bending test. And it was shown that there are parameters showing high sensitivity to fracture pattern. And this is the average frequency, rise angle. This is this angle again, energy and duration. So as you can see, the tensile mode of crack, which includes opposing movement of the cracks, results in, again, short rise time and higher frequencies. So they are, for example, they can be put in certain parts. Like with the laboratory experiments, it's possible to make some kind of relation between them and basically put like if we plot the average frequency versus raise angle, we are able to define a line which is separate those two types of events. And as you can see, this is not as clear on the other parameter settings, but they are still quite nicely separated. And in case of laboratory experiments, the population of tensile and other signals can be well distinguished with a single diagonal line, both if we use the resonance sensors and broadband sensors. But this is something that has to be, the line is not something that we use. It's not one line for every kind of event, so it should be adjusted to every single experiment separately. So still, this is something that is mostly used in laboratory experiments and not much in the real monitoring applications. But it's still possible even with just a simple parameters obtained from the waveform. Another thing is, as I mentioned at the very beginning, Kaiser effect and also the felicity ratio. This is something that maybe some of you already heard. We have, let's say we have a specimen, and this is the plot with the vertical axis is the cumulative acoustic emission activity, and on the x-axis is the load. So during the increase of the mechanical load in a specimen, in case of Kaiser study, that was metal, but it also applies to different materials. It is normal to record increase acoustic emission activity due to possible development of microcracking. So let's say we go to a moderate load level P1. In case afterwards, when we're doing unloading and reloading again, there is no new acoustic emission observed. Obviously, having in mind that we have the same sensitivity level and the same threshold. And this happens until we reach the previously maximum load P1. And when we overpass, we start to have new acoustic emission happening. So this is so-called Kaiser effect, and can be practically explained by the fact that the damage associated with the stress level P1 has occurred during the initial loading, and therefore there are no extra damage. Consequently, there is no new acoustic emission happening in the reloading phase. So in simple words, it means that the material is quiet until it's pushed harder than it was before. But if we go further and we increase and we're reaching a moderate, serious damage level. So for example, in this case, this is P2. In case of unloading and reloading again, we see that the acoustic emission starts at loads that are lower than the previously maximum one. And this is so-called a felicity ratio. This is the ratio between the P3 and P2. It's called felicity ratio, and is a kind of indicator whether the material is intact or there are some kind of accumulated damage. So if the felicity ratio is around 1, the Kaiser effect is valid and the material is assumed to be intact. However, the lower we get with the ratio, the assumption is the more damage we accumulate in the material. So another ratio that we use with the parameters that we obtain from parameter-based analysis can be the calm ratio, and basically this is the total activity during unloading, so the red parts, over the total activity during the whole cycle, so both loading and unloading. And basically this gives us an indication that if the calm ratio is around 0, so meaning that we don't have activity happening during unloading phase, we have a structurally stable material. However, with the increase of the calm ratio, we have the accumulation of the damage. So basically, in short, like I will not go into much detail, but for example, combination of the calm ratio and felicity ratio give us an evaluation of the material condition, because we start to see what's happening during the unloading phase and loading again, and we can see that if the activity is more, meaning that there is a degradation of the material. Another thing that is based on the parameter evaluation is the B-value analysis. This is coming strictly from seismology, and it's not very commonly used, but it's there. So basically the assumption for the B-value analysis is that the change in the B-value indicates the change in the concrete cracking behavior. It's this analysis describes an overall patterns of a large number of events statistically, yeah. And we use here, we characterize large numbers of events, for example, like in seismology, obviously earthquakes, but in this case, acoustic emission, using an empirical log linear frequency magnitude distribution. In case of acoustic emission, this is not necessarily magnitude, but amplitude, but I will show it a bit later. In theory, for the structural health monitoring, we need only one sensor for this kind of analysis, but in general, the more would be probably the better. But in theory, one sensor is enough to perform this analysis. And the idea is that the drop in the estimated B-value is a good predictor of the point of maximum applied total force. So to give you a bit more insight into it, so basically we have this relation, and from this where ML is a local magnitude, this is the seismology equation, which is adjusted for later. In the next slide, I show you how it's adjusted to the acoustic emission events. But let's say we have a magnitude of an event, which is a measure of the amount of energy released during an earthquake or an acoustic emission event. In case of earthquakes, it's dependent on the distance, but in acoustic emission, we don't take it under consideration. And in here is the number of earthquakes / events with the magnitude higher with the defined local magnitude. And A and B are empirical constant. A is the value where the line is crossing the x-axis, and B is the slope. And the moment the place where the function deviates from linear trend is showing the network sensitivity. So after this point, we cannot reliably consider the signals in this analysis. So in case of application in material science, this is an example. So as I said, like in this case, we don't use magnitude per se, but we usually use the heat amplitude. And then we call it not magnitude frequency distribution, but amplitude frequency distribution. This is the equation that is used to evaluate the amplitude of the signal. And the idea is, for example, in concrete application, that decrease, I think I mentioned this before, a decrease in the B value below a value of approximately 1 may indicate that the stresses are redistributed and the cracking is more localized. So this is an example from a study from Thomas Schumacher. And basically, they were doing experiments on the reinforced concrete bridge griders. And when they were applying service load, the B value was around 2. However, if the load was increased and they reach overload, the B value reached much lower level, and it was even below 0.5. So this was the indication for the damage in there. Okay, so just to give like the brief overview about the parameter-based acoustic emission, there are some advantages and disadvantages. So basically, the advantage is definitely that we need less storage space. It's much faster analysis, which also indicates that it's computational inexpensive. It's very simple and does not require a lot of sensors. Like in some cases, even just one is enough to perform the analysis. It gives also the real-time analysis, and it's cost-effective. On the other hand, it's based on idealized assumptions. So this is also worth keeping in mind, that we assume that the nature of the source, we have a point nature of the source, and also that we have a linear behavior. And some information is also lost. It's impossible to make elaborated analysis. We have, in this case, also limited view on the physics. And what is very important is that settings and sensor type affect the results. For example, like if we define threshold crossing slightly different, we have much different results of both counts, the number of hits, and so on and so on. So therefore, the comparison between data sets is relatively difficult. So key takeaways from this part is that the parameter analysis is based on extraction of features that contain most of the waveform information without the need to store the whole number of waveform data. We have a Kaiser effect, meaning that there is no acoustic emissions, new acoustic emissions until the stress surpasses the previous highest level. We have calm ratio, that is the total activity during unloading over the total activity during the whole loading and unloading cycle. And we have also the B-value analysis, and the change in the B-value might indicate a change in the concrete's cracking behavior. Okay, so that was parameter-based, and the other thing is the signal-based approaches. So basically, as in contrast to the previously explained, the signal-based use the entire waveform of the acoustic emission event to do the analysis. It contains much more information, therefore it allows to improve the interpretation of fracture process. In general, we have two signal-based approaches, which is waveform analysis and quantitative analysis, which are originating from seismology. And those two are quite wide subjects on its own. So as I mentioned before, I will just briefly give you an overview over those because it would be a whole lecture on those stuff if necessary. But things that are important to keep in mind that those analysis, they're dependent on the type of the sensor, on the coupling, and it's very important to keep in mind that the recordings have to be synchronized to obtain reliable results. So first are the waveform analysis, and in this in this part of the analysis, the changes observable within recorded signals can be the idea is that they can be associated with the changes in the structure being monitored. We analyze the whole waveform and we compare them with each other. It's suitable for application of machine learning and artificial intelligence since we have the whole waveform. And this part does not rely on the 3D localization in contrast with the next analysis I will be talking about. In theory, it can be performed with a single sensor. However, it's advised to use more sensors. And we have two types, basically main types. We have a frequency analysis and waveform correlation. So as I said, there are several types. I will not go into very much detail, I'll just list them so you have a general overview. So we have a waveform correlation. We have different types of time frequency analysis, like a wavelet transfer or a short time Fourier transfer, or other types of time frequency transfers. There is plenty of them. This is an example of a wavelet transfer of an acoustic emission signal. You can, the axes are not very visible, but yeah, we have time frequency axis. We can look at the dispersion of the wave or whatever anyone wants. And there is a potential for machine learning based approaches like pattern recognition or matrix decomposition techniques or neural networks for acoustic emission localization. But coming to the second part, we have also the quantitative analysis, and the goal of them is to describe the nature of acoustic emission source as accurately as possible, rather than concluding about their effects measured at the sensor location away from the source. So this is a quite sophisticated approach and requires a high fidelity network of sensors and a sophisticated time-consuming analysis. So it's mostly used in laboratory because there are quite high requirements on the equipment, computation, and also interpretation. So we need relatively simple objects to give a proper interpretation. An example of such analysis is source location and source inversion techniques such as first motion technique or moment tensor inversion, which I will, source localization I will say in the next part, but here I will briefly mention about the moment tensor inversion and what it is. So since quantitative analysis relies on inversion methods, it's worth introducing the concept on inversion. I guess you're familiar, but just for the reminder, the forward problem starts with the causes and then we calculate the effects, while the inverse, so this is where we are, but inverse problem analyze the effects and aims to estimate the causes. So this is what we have. In the inverse problem, we have a model. A model is assumed to approximate the physics of the problem, and the model parameters undeterminate from the data. So this is the idea. I will not go into details with this, but just to give you the overview. But what I want to stress out that in those quantitative methods, a very important thing is a proper estimation of the first arrival of the P wave. And often use the threshold crossing is not enough for this kind of analysis. It's not sensitive enough because, for example, I don't know, the threshold might be higher and still record the data, but the first arrival is much earlier, and that introduces a lot of problems in a way. What is commonly used in acoustic emission, since we have a lot of data, a lot of waveforms, it's impossible to do the manual picking with the whole data set. The commonly used tool is the ACAICA information criterion called AIC picker. And basically this works in such way. We have, it's a mathematical approach. We have a function called the AIC function, and where the minimum is, we have the P wave onset. It's working much better if we have a good signal to noise ratio. As you can see, that there are two examples in a clean signal and in the noisy signal, that the minimum is not as clear as in here, but still this method is not perfect. There is a lot of bias that can be also introduced in here, but yet this is the fastest and the most commonly used way of picking the first arrival. With this, okay, so we have the first arrival, and just to give you a brief overview about the moment tensor inversion, the goal of this method is to use observed values of ground or surface displacement to infer properties of the source. There are 3 different types of moment tensor inversion methods. It's absolute, relative, and hybrid, which is a combination of the two. And this is coming from seismology, obviously. They differ greatly according to the available data and purpose of the studies. And for example, the absolute method requires calculation of the theoretical Green's function for each event, whereas the relative doesn't. And this is, for example, the main difference between them. And the hybrid one is kind of combining the two of this. So basically, based on the methods used to estimate Green's function, we describe it's based on the methods used to estimate the Green's function, which describe the wave propagation between the source and the receiver. So this is for the seismology, but in the case for acoustic emission, it's not, it has to be modified to be applied to these cases. And for this, in concrete, it's the method used for estimation of moment tensor inversion is called simplified Green's function for moment tensor analysis. In short, it's sigma. It characterizes concrete cracking in 3 different types. So you have either tensile, shear, or mixed mode. So this is how it's represented. It's an absolute method and uses only the P wave arrival time and amplitudes in time domain. But for this method, we need at least 6 good acoustic emission signal to perform stable and reliable results. And actually, it's better to use more sensors if in case we have a high noise level, then we need more sensors to get the results. And this is one of the examples of application. Again, a 4-point bending of a beam. The sensors are quite like maybe not densely, but there is 6 sensors installed on the beam, and as you can see, different in here, like different types of crack have different colors, and they're this is the program that uses this, and they're kind of it's possible to evaluate the mode of the crack in the bending test. So I will not go into detail into this as well, but just to show that there are tools that are that make it possible. Again, it's mostly used in laboratory experiments, and yeah, requires a lot of good data to be able to perform. So basically, the question would be which one is better. So we know that the moment tensor inversion has been used in seismology and mining to characterize ground motion for many decades. However, it has still not found a widespread application and acceptance in fracture monitoring for civil engineering materials. And some of the reason for this might be that it's associated with like that the wave characteristics are somehow easier to interpret in large scale media of Earth, and it's difficult in small scale, for example, concrete. It's also the instrumenting civil engineering structures, for example, with high fidelity sensor and recording hardware is very expensive, cumbersome, requires highly specialized expertise for analyzing and interpreting the data. So sometimes it's just not, it's not worth it, basically. So yeah, so we have parameter-based analysis, which are faster, computationally cheaper, less data, good for statistical analysis, but we don't store signal. And we have signal-based, which require more sensors. Like usually, we have a big data problem, time-consuming, but nowadays it's more available due to the technology development. So it's increasing, the interest in this type of methods is increasing. So basically, the answer which one is better is hard to, the question is hard to answer because they are used for different applications. So different applications require different needs, and for example, for laboratory tests, it's maybe better to use signal-based, but for monitoring of a big structures, it's easier and more cost-effective to use parameter-based. Okay, to sum up this part, I know it might be a little bit chaotic in here, but we have a signal-based acoustic emission techniques, which use entire transient waveform of the acoustic emission event. We have two main types of the approaches. We have waveform analysis, and we have quantitative analysis, source location and moment tensor inversion. It's very important in those analyses, the type of the sensor that we're using, the coupling, and the synchronization of the recordings. And in concrete, with moment tensor inversion, we can characterize cracking in either tensile, shear off, or mixed mode. Okay, and coming to the last part of the presentation, I will briefly talk about the source localization methods. So the goal of those techniques is to associate an acoustic emission event formed from a collection of acoustic emission signal, as I mentioned before, hits that arrive within a certain time window with a physical cause. So we want to get what we record associated with one physical cause happening inside of our material. Basically, mostly localization techniques are seismology-based and can be applied to acoustic emission with minor modification. It's an inverse problem. And the crucial part of this is the accurate estimation of the arrival time. When I was looking at this subject, I found that there is a lot of ways to describe the localization, but this is one that is, I think, the most commonly used. This is a classification from paper of Ge from 2003, where he divided in such way. So we have two main branches. We have triaxial approximation and arrival time approaches, which is our main interest. And then from this, we have a point location. So we want to look at the exact point where the source is nucleated, and the zonal location, which is used for fast estimation where the event might occur, but we look at the zones, not exactly the precise location where it is. And then in the point location, we have either non-iterative methods and iterative methods. And the one that I'm going to talk a bit more today is the Geiger method, because this one is the most commonly used for estimation of the source location. And the principle of this method is to minimize the residuals R between calculated and observed arrival time at each sensor. So basically, the method relies on the sensors. We need at least 4 sensors to localize an event in a 3D, because we have 4 unknowns. We have the X, Y, and Z coordinates of the source, and also the event time, so when the actual source happened. And for the inputs, we have the sensors locations. We have the arrival times at each sensor. And we also have the wave speed. This is usually the P wave velocity at which the wave travels through the material. So how it works, basically the first step is that we assume some kind of initial guess. We start with an initial guess for the event location and time of it. And this could be a random point inside the volume that we are considering, or based on rough calculation. This doesn't matter that much, but it rather should be inside the array. Then we calculate the predicted times. Using the guess location, we calculate how long it would take for the wave to reach each sensor, assuming we know the wave speed. And this we, for example, get from ultrasonic measurements or from other ways we calculate that. Then we compare the predicted and actual time. So for each sensor, we compare the observed time that we have with the calculated with the location of our source that we just got. And then we adjust the guess. So basically, we adjust the guess location and time to minimize the difference between the predicted and actual times, and we iterate. So basically, we repeat the calculation and adjustment process like many times until we reach the predefined error value, which are basically as small as possible. So this is basically how it works, and we do it all the time until we reach our minimum. However, this method is relatively fast, but it has source of a lot of uncertainties. We have errors in the picking of the arrival time. As I said, the IC picker is usually used, but this is not ideal method. Sometimes it's not picking well enough, and if we have a lot of data, we might sometimes not get the right, we don't check data one after another usually, so this might introduce some uncertainties. Also the P wave velocity, as I said, like it, for example, comes from ultrasonic measurements, but with the damage accumulation, it might change, so it's also important to take it under consideration. We assume in this method that the travel, like we have a straight travel path, but it's not necessarily true in a cracked, heterogeneous, and anisotropic materials. The number of sensors, also the signal-to-noise ratio, which is not maybe directly connected with that with the method itself, but for example with the peaking of the first arrival. And the equation generally assumes that the material is homogeneous and isotropic, and that the acoustic emission source can be modeled as a point source. And just to give you an example, for example, this is a localization of events inside the concrete cube. We had 6 sensors, and we have 2 different types of materials. In one, you can see the sources are localized within the material, where in the other one, there is a lot of events that are localized outside. And this is connected with the fact that, for example, the material that has a good localization accuracy is like a nice concrete, and the other one has some kind of, during the hardening process, there was a lot of bubbles happening on the surface, which are not happening inside, but those are some kind of a different acoustic emission events, which are not fitting in the assumption of the Geiger method, and therefore we have, due to the surface effect, we have a low localization accuracy. There are also other methods that are based on neural networks or probabilistic approaches like nonlinear log, widely used in seismology, direct algebraic methods taken from GPS technology, or time reversal methods, but I will just leave it out there for you to know, but this is way too much to talk now. So just to give you the key takeaways from this, proper source localization is necessary for quantitative methods in acoustic emission, and most acoustic emission localization methods were developed in the framework of earthquake seismology, however with some kind of minor modification that can be easily applied to localization in material science. And there are plenty of sources of uncertainties in the localization techniques, such as picking the first arrival, estimation of velocity, or travel paths, and so on. Okay, so I'm at the end, so to just give you the sum up, conclusion, outlook, whatever. And I think the good way to do the sum up of this is to give some kind of advantages and disadvantages of acoustic emission as a method in general. And why is it great? It's a passive and non-invasive technique, and we can observe the damage during the entire load history, and we can monitor this process during this time. It's great for detecting new cracks and propagation of the old ones, and can detect also cracks at the very early stage of its nucleation. And it's also possible with the method to characterize the fracture mode, estimate the source location, and as I mentioned before, it's very sensitive, so we can detect even very tiny events inside the material. And what is also quite nice, compared, for example, to ultrasonic methods, the relative position of the sensor defect is not critical in this case. However, there are some disadvantages. The method is only capable to detect new cracks or new processes that are happening. If nothing is happening, basically we don't have any kind of acoustic emission, so we cannot do anything. It's also not perfectly reproducible, and it creates a lot of data, so this is a big data problem at the moment. It's very sensitive, and this is great, but it's very sensitive to noise and signal attenuation, so this is also important to keep in mind. And there is a low, the acoustic emission are of very low energy. So this is also some disadvantage. And in general, it's great, but I think the best, it's not a method that can be ultimately used alone. It's best if combined with other methods, and therefore this is possible to obtain the whole picture of what we want to achieve. And just to give you some outlooks, there is plenty of new areas where acoustic emission can go and where it can develop. As I said, it's a big data science, so it's a great potential for machine learning and artificial intelligence necessary for development is necessary for the progress in this area. And also those two, machine learning and AI, can be applied to localization or discrimination between acoustic emission and noise, which is kind of an important area to be developed as well, and also to determination of different types of fractures. Also, acoustic emission in structural health monitoring, it's ongoing, it's happening, but there's also a lot of places where it can be improved for evaluation of the aging of the structures or component, and to detect defects at very early stages. So it helps with maintenance of the structures. And also another thing, it's a great tool for digital twin technologies for structures as bridges, tunnels, machines, and wind turbines, which is currently quite a big topic as well. Okay, so I think this is the end, and thanks a lot for the attention.
Thank you, Anna, for this very nice overview about acoustic emission. I think we have a few minutes for questions, so I will stop the recording and give room for discussion. Let me stop.